Okay, this time we have node voltage problem. Let's say this is NV1, node voltage number 1. Okay, we will use node voltage technique to come up with a matrix containing KCL equations to solve the circuit. This circuit has inductor here, and the inductance is 0.01 Henry. And let's see, this is Henry 8. Sorry about that. Wait a minute. Let me clean that up, okay? It's a little bit dirty here. Okay. This is 0.01 Henry. How about that? Okay, that's better. Here is a dependent source. Excuse me. And here we have a resistance. Diagonal path. Here we have another source. This is I sub S, current source. And here we have capacitor of capacitance 0.05 farad. And let's see, we have another resistance here. Excuse me. We have a resistance here. We have an inductance here. We have another source. This time this is a voltage source, P sub S. And we have a line going like this. Let's start with the bottom here. This is our reference node as defined by this grounding symbol. Number 1 node is here, and this is a voltage dependent voltage source, or shall I say actually current dependent, because that's a 4IA. Current dependent voltage source. What is I sub A? That is the current flowing this leg. And this is 0.5 ohm resistance. This is node number 2. Here is node number 3. In between we have 0.01 Henry, again an inductance. Well, on the top we have 0.5 ohm, and this is a node number, that's the same as number 3, and this one is node number 4. Alright, so let's recap the circuit. We have multiple sources in this circuit. One current source I sub S, one voltage source V sub S, S meaning the supply of course, and we have a dependent source which is 4IA, so the output, which is a voltage, is dependent on the input, which is current I sub A. I sub A is the current that's flowing from node number 2 onto the ground, and the path has 0.5 ohm resistance. On the left we have 0.05 farad capacitance, and above it we have 0.01 Henry inductance. Alright, so what is the task here? The task is to come up with a matrix that describes this circuit using node voltage method. So we're going to use the current law given by Gustav Robert Kirchhoff. So the relationship here we have is I sub C is the current passing through the capacitance is C dVc dt, or shall I say, using the operator notation, C times capital D P sub C. So this is one important rule of law. The next one is from the Faraday's law, which gives us the voltage across an inductor as L dIL dt. And we can recover the current passing through the inductor by inverting the differentiation. Namely, we will have I sub L is equal to 1 over L d minus 1. Notice d minus 1 is the inverse process of differentiation. So primarily it's integration. So we are looking at Faraday's law in this form. Why do we need these things? Because our circuit has capacitance as well as inductance aside from resistances. So we will need these expressions. Now when we go back to this circuit, in the diamond we see I sub A. So the first thing is to figure out what I sub A really is. I sub A is the current that's flowing from node number 2 onto the floor, and it passes through the resistance 0.5 ohm. So using Ohm's law, what we get is I sub A is the voltage drop across this resistor, which is 0.5 ohm, divided by the resistance itself. The voltage drop, of course, is P sub 2 minus P0, which is 0 itself, so P sub 2 underneath 0.5. Meaning, I sub A is, let me write this here, I sub A is 2 times P sub 2. The 2 is coming from 1 over 0.5, of course. All right. Next, what we see is between nodes 1 and 2, the voltage drop is V sub 1 minus V sub 2, and that is equal to 4 I sub A. The reason we have V sub 1 being positive and V sub 2 being negative is based on the fact that node 1 is on the plus side of this diamond and node number 2 is on the minus side of the diamond. We just got the expression for I sub S, which plugging with 4 times I sub A will be 4 times 2P2. So that will give us 8P sub 2. Meaning we have now V sub 1 minus 9 times V sub 2 equals 0. Well, this will give us the first box to go into the matrix, such as the following: 1 times V sub 1 plus minus 9 times V sub 2 plus nothing times V sub 3 plus nothing times V sub 4 equals 0. Our matrix would have 4 elements, V1, V2, V3, V4. Okay, so let's look at the supernode 1 and 2. Supernode and supernode SN maybe. All right. 1 and 2. Why? Why did we pick up the supernode? Because when we use the node voltage method, we have to figure out the currents flowing from any of these nodes. But at node 1 or node 2, we have a voltage source hooked up. Having a voltage source doesn't tell anything about the current flowing. So we would like to avoid having to go through that path. In other words, we will group 1 and 2 nodes as one bigger node, super node, super duper. So given that, now we have to figure out the current flowing along each of the legs connected to the super node. So the one we see immediately is the current through the capacitor, I sub C, C, D, V, C, D. So meaning, using that and the capacitance being 0.05, we get 0.05, and then D, the voltage drop is V sub 1 onto the floor, so simply V sub 1. So that is the current flowing via this capacitance. Next is the current flowing via the resistance, which is primarily I sub A, and as we know, that will be simply 2P sub 2. Okay, I sub A is 2P2, remember that. Then we have the current flowing via the inductor, and that will be 1 over L, 1 over 0.01, and that will be simply 100, right? And then D minus 1, the voltage drop between 2 and 3 is V2 minus V3. Using, of course, the house rule, which says wherever you are, you're at the top. So the current flows from node number 2 onto 3. Next, we have to figure out the current flowing via zero point 0.5 ohm onto the node number 4. So that will be V2 minus V4 divided by the resistance on the path, which is 0.5. So that's also taken care of. Next comes the current that's flowing away from node number 1 onto node number 4, which is I sub s, leaving the node. So using passive sign convention, that's a plus IS. What is left now is the current flowing through the inductor 0.01 Henry. And again, that will be 1 over L. So 1 over 0.01 is plus 100. D minus 1, so V sub 1 minus V sub 4. So that will take care of all these branches connected to the supernode. We have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 legs connected. So we got all of them counted. Next is simply simplification of this expression, which is then 0.05 dP1 and plus 2V2 plus 100 D minus 1 inverse, of course, V sub 2 minus 100 D minus 1 V sub 3, then plus 2V2 minus 2V4 plus I sub s plus 100 D minus 1 V sub 1 minus 100 D minus 1 V sub 4 equals 2. This is a large expression, but nothing we cannot handle. So this is giving us another box. Let's be careful here to write each and every term carefully. So this box would be large box. Okay, I'm going to draw this large box here. This is going to the matrix, as we said. The first thing is those with V sub 1, 0.05 D plus 100 D minus 1. How about that? Both with V sub 1. Then the next is with V sub 2, which is 4 plus 100 D minus 1, and then V sub 2. Let's pull this thing. Next, we have those with the V sub 3, so plus minus 100 D minus 1 V sub 3 plus minus 2 minus 100 D minus 1 V sub 4 equals minus IS. Lot of terms here. We got it all. So what now? The next thing is to realize that the voltage at the node number 3, V sub 3, is simply V sub s. Why? Node number 3 is not the same as the floor reference node 0. It's different because there is a voltage source stuck between the reference node and node number 3. So node number 3 has a plus side of the voltage source Vs, meaning it's taller than the ground by the amount that is stuck in between, meaning V3 is Vs. Okay, long story short, we have another box here. So this box would have no V sub 1, no V sub 2, no V sub 4, meaning we would have to write nothing times V sub 1 plus nothing times V sub 2 plus 1 times p sub 3 plus nothing times, wait a minute, this is 3, okay? Oh, looks bad. Let's see what we could do. Wait a minute, no. We can do this p sub 3, all right, there you go. Plus nothing times p sub 4 equals p sub s, there you go. Finally, this third box. We have one more box to collect. To do that, let's apply KCL to node number 4. So KCL at node number 4. That would give us the following things. IS is coming to the node, so minus I sub s using passive sign convention. And the voltage V sub 4 and V sub 2 will give us the voltage drop V sub 4 minus V sub 2 using house rules. So current goes away from the node. Down below we have 0.5 as the resistance on the path. In like manner, V sub 4 minus V sub 3 underneath. Resistance on the path is 0.5 again. What else? We have another path going to node number 1 via the inductance. So that will give you plus 100 d minus 1 p4 minus p sub 1. So equals 0. All right. Once again, we have to simplify this expression carefully. So what we have is minus is plus 2v4. The 2 is coming from 1 over 0.5, of course. Minus 2v2 plus 2v4 minus 2v3 plus 100 d minus 1 p4 minus 100 d minus 1 p1 equals 0. So this is going to give you the last box, folks. Okay, so this would be quite a few terms, but let's see. Those where V sub 1 will be gathered the first. So we would have minus 100 d minus 1 V sub 1. Next, we need those with the V sub 2, and that's going to be minus 2 V sub 2. Next, we need the one with the V sub 3, which is minus 2 V sub 3. Next, we have 4 plus 100 d minus 1 V sub 4 equals IS. So this is our fourth box that will be eventually going to our matrix. So we got all these 4 members, so the matrix is coming up here. Let me write this. 1 minus 9 0 0. Too much crowded here. Let's be careful, folks. A lot of things to fit in here. That looks a little bit bad, but this is V sub 1 and V sub 2 and V sub 3 and V sub 4. Okay, the one on the top is 0. Next, we have a bigger guy coming here, 0.05 d plus 100 d minus 1. Too many things. 4 plus 100 d minus 1 minus 100 d minus 1. Too many things, of course. Minus 2 minus 100 d minus 1. It will be minus is. Okay. Next, that one is easy. 0 0 1 0. That will give us V sub s. Again, a little bigger number, minus 100 d minus 1 minus 2 minus 2 4 plus 100 d minus 1, I guess. So we have 4 by 4 coefficient matrix, okay, which is, as it turns out here, admittance. This is admittance times the voltage vector is the source current. So primarily Ohm's law expressed in the matrix form 1 minus 9 0 0 0.05 d plus 100 d minus 1 plus 4 plus 100 d minus 1 minus 100 d minus 1 minus 2 minus 100 d minus 1 and then minus is on the other side 0 0 1 0 ps on the other side minus 100 d minus 1 minus 2 4 plus 100 d minus 1 p for is is. Okay, that's about it. Hope you enjoyed it. I had a whole lot of fun. Alright, take care.